So we've been talking about acid deposition. That's what you guys looked at with the maps. And acid deposition, the reason we call it acid deposition and not just acid rain is because it could be rain, it could be snow, or it could just be particles that end up coming down and landing on the surface of the earth, whether they're landing in water or they're landing in terrestrial ecosystems. Typically, it's going to be precipitation that's acidic. Now, you need to know that the pH is less than 5.6. There have been quite a few questions on AP exams about the pH of acid rain. Normal rain has a pH of 5.6. If it's less than 5.6, it means it's more acidic than 5.6. How does it form? The two things you guys looked at on those maps were NOx and SOx, right? NOx and then SO2. Those are the two components that make up acid rain. And what happens is they convert from a primary pollutant, a pollutant that's emitted by a smokestack, into a secondary pollutant, one that reacts with a chemical in the atmosphere. So they react to form nitric acid and sulfuric acid, hence acid deposition. They're creating these acids, right? If you remember looking at those graphs, you saw that between 1990 and 2000, or 1970 and 1990, the amount of these pollutants was greatly reduced. So the Clean Air Act has done a lot for reducing emissions of certain types of pollutants. It's actually one of the most successful pieces of legislation that we have in terms of environmental impact. A lot of other legislation and stuff that we end up passing ends up not doing a whole lot for the environment. The Clean Air Act is one of the biggest successes that the U.S. government has had. So how does it affect the environment? In plants, it damages the leaves of plants. It literally burns them. And it also leaches soil nutrients. So it takes those soil nutrients out of the environment or out of the soil and makes them not available for plants. I'll show you some pictures of trees that have been affected by acid rain in a minute. In aquatic habitats, it mobilizes metals. Okay, what does mobilize mean? Mobilize means it moves metals into the water stream, and it ends up becoming toxic to many organisms. Let me show you an example. If I have carbon dioxide, CO2, and all of a sudden a pollutant comes along and kicks off an oxygen, now I have CO, which is carbon monoxide. It's going to be a lot more hazardous. Same thing happens with aluminum. Aluminum is going to be attached to a bunch of other different molecules, but if that pollutant or if that acid rain comes in and kicks it off, all of a sudden it's going to create more toxic chemicals. Okay, that aluminum is going to become more toxic because it's free in that water, and too much aluminum is going to be hazardous to many of the organisms. And then any type of building or monument is going to end up getting destroyed by some of these acid precipitation events. We don't see a lot of this anymore because of the regulations that we've put on nitrous oxide emissions and sulfur dioxide. But 100 years ago, we saw a lot of this statue or buildings that ended up being degraded because of the acid rain. So here is some damage from plants from acid rain. You'll notice over here on the left, we have needles that look really brown and brittle. They're about to die. Here we have an example of two different forests that have been affected by acid rain, and they pretty much have killed the trees there. So acid rain can be a big problem. And the problem too is that a lot of times this pollution can be carried elsewhere. So it doesn't necessarily mean that, oh, because we're polluting in Wisconsin, we're going to get acid rain here. we could be polluting in Wisconsin, and then the weather system carries it over to Maine, and it ends up producing acid rain there. So where is acid deposition a problem? We looked at these maps. Northeastern U.S. What do we know about the northeastern part of the U.S. compared to the western? Industrialized. Think about history. Big cities. This is where we settled, right? If we think about population density, it's higher over here. Okay, these are where the major power and industrial plants are, all in the northeast. Now, your graphs didn't look, or your maps, you saw a lot more right here. Okay, not as many up here, but this is where they have all of the major power plants, and the reason they have so many of them, or more than other parts of the U.S., is because there's typically a higher population density that lives in the east, right? Cities are closer together, there's more people living closer together. Whereas out west, there's a lot fewer people and they're more spread out. So here's what we're going to do. We are going to move into climate change. We'll be doing some coloring in a minute, but I'm going to give you your new note packet, and we will go from there. The climate change unit is pretty straightforward. It's not as complicated as like air pollution, because if you think about air pollution, you probably haven't talked a whole lot about nitrous oxides, right? So you're having to learn all these terms. With climate change, there's not as many terms to learn. And typically, you've heard of some of these things before. A lot of people could tell you, oh, the polar bears in the Arctic, right? You've heard the word climate change. A lot of you talked about it in bio. And that's kind of what we're going to be looking at. You do need to know air pollution really well, though. Air pollution and water pollution, and then hazardous waste accounts for 25% of the AP exam. So climate change is not necessarily a part of that. Climate change is on there, but it's not as prevalent. Also, if you are planning on signing up for the AP exam, you need to do that today. Okay, you only have a couple days left to sign up. So there are quite a few of you who were planning on signing up who have not yet. All right, so climate change. Global climate change is our topic. So the first thing is climate change, or global change in climate, occurs naturally. It happens all the time. What are some of these things that influence natural causes or natural changes in our climate? Volcanoes. We're going to talk about volcanoes. Volcanoes can actually cause the Earth to cool based on the gases they emit and because they produce so much soot. Variations in solar energy, the amount of sunlight or energy coming at us from the sun, that can change how much our Earth is warming or cooling. And changes in greenhouse gases. You guys saw that methane is a greenhouse gas. Most of these greenhouse gases are naturally occurring. So because they're naturally occurring, they can also fluctuate as well. So I'm going to talk about this graph in a second when you're done writing. We also have Milankovitch cycles, which are named after a scientist with the funniest name, Milankovitch. And these are periods of normal warming and cooling because we have changes in our orbit, right? So the orbit around the sun, sometimes we might be slightly closer to the sun, and sometimes we might be slightly further from the sun, and our orbit isn't the same every single year. Our orbit changes slightly. And so we get these cycles where sometimes we're slightly closer to the sun and sometimes we aren't. So that's something to think about as well. If we look at this graph, this shows us the last 800,000 years. Notice, our temperature is going up and down and up and down. How did they figure out what the temperature is from a long time ago? Anyone know? How would they figure out temperature from a long time ago? Okay, fossils, carbon. So what they can do is they can use tree rings, right, if there were trees around. What they also do is they can use ice cores. So they drill a big ice core, because if you think about Antarctica, when does Antarctica melt? Well, only if there's climate change, right? But it hasn't really melted in the last 800,000 years. So what they do is they dig these ice cores, and there are little tiny bubbles that are trapped in the ice. And those little bubbles have the air that was trapped in there from a long time ago. So it's literally a record of what the air was like. And they can figure out, based on the percentage of carbon dioxide, what the temperature is or was in the past. So we can see that here. Take a look at this graph. This is temperature, okay, in red. Carbon dioxide in blue. This is the last 400,000 years. Notice, CO2 has never been above 300 parts per million in the last 400,000 years. Guess where it's at right now? Up here. Okay? So if we look at what our current CO2 is in the atmosphere, there is a page where you can go to, and it'll tell you. Currently, we are at 411.75 parts per million. When I was back in college, there were a lot of people talking about keeping it under 400 parts per million. We have surpassed that. A while back, there was an organization that was talking about keeping it at 350 parts per million. Okay, again, we have surpassed that. And if you look at this graph here, this is over the last 60, 70 years. From 1955 to present, we have increased by 100 parts per million, from 310 to 410, okay, in the last 70 years, okay, increased by 100. So the carbon dioxide in our atmosphere is increasing, and we can see that that parallels with the temperature, because every time the carbon dioxide goes down, the temperature goes down. Every time it goes up, the temperature goes up. So a lot of these changes in CO2 and in temperature are thought to be a result of anthropogenic or human causes, like burning fossil fuels, clearing forests, creating fertilizers. All right, so the temperature is increasing, the CO2 is increasing. All right, and we have dubbed this climate change. Now, you don't need to know the difference between climate change and global warming for a test, but I have it on there because you might hear the difference between the two, or you might hear both of them and wonder what the difference is. So climate change is talking about all the changes that happen in the climate, precipitation, storms, oceans, how it all changes as a result of humans burning fossil fuels. Global warming is just talking about the warming temperature due to fossil fuels. Very similar. Okay, this one is more broad. Most people nowadays use the word climate change instead of global warming. Global warming was the more kind of outdated term a while ago. But the reason people prefer climate change is because it encompasses a lot more, and it recognizes the fact that not all parts of the globe are warming. You do not need to write anything down for this, but this is the history of global warming. In 1840, some scientists talked about how clear-cutting forests had some effects on the environment. That was it. Okay. 1896, a Swedish chemist says, hey, when we burn coal, it's evaporating it into our atmosphere. Again, they didn't know what pollution was. They had no idea. Then we get to the 1960s. A woman by the name of Rachel Carson wrote a book called The Silent Spring, and it's talking about pollution. And this was really kind of the wake-up call. So in 1969, global warming first appears in a New York Times article. You guys know about the 70s? What do we know about the 70s? Hippies, right? Hippies are the reason that we have all of this environmental stuff. They were the ones that first kind of pushed for the environment to be taken care of. So we have the first Earth Day in 1970, formation of the Environmental Protection Agency. In 1985, the hole in the ozone layer was identified. Okay, and then we get to 97 and 2005 in the Kyoto Protocol, which we'll talk about. Basically, all these nations around the world decided they were going to lower their greenhouse gas emissions. Well, the United States participated, but guess what? The United States was the only country that did not sign it. So all these other countries, 150 of them, many of them developed countries, all decided to sign this and say, hey, we recognize climate change. The U.S. did not. So we'll talk about that when we get there. So we're going to talk about the greenhouse effect. Now, greenhouse gases are good. We need them. All right? Greenhouse gases are like a blanket. Sleeping with a blanket on at night is comfy, right? Our planet would be super cold if we didn't have greenhouse gases. But every time we pollute, we're adding more greenhouse gases into the atmosphere. How would you like to sleep with 12 blankets on top of you? Okay, it's going to get a lot warmer, right? So the greenhouse effect is talking about how the sunlight comes in and then these gases trap it in here. And that's why we're getting the planet warming. So we're going to write this down and then we will color. So what happens here? We have UV radiation from the sun. It ends up striking the earth. So UV radiation is sunlight. Okay, it comes down and it hits the earth. So sunlight, and you can remember that because you know UVA, UVB rays. A third of it is reflected back to space. So some of that sunlight's reflected back, but the rest is absorbed as infrared radiation or heat. Okay, and the greenhouse gases trap this heat in, preventing it from going back into space. So more greenhouses mean more of that heat is going to get trapped inside of the atmosphere. So once you're done writing that, flip to the next page. We're going to color. So on this diagram, we are mapping out or showing the greenhouse effect. So the first thing you're going to need to do, one person can start by coloring this arrow yellow. Okay, so grab the yellow. This is all the sunlight coming in. The other person can color the ground green, showing that this is the ground. And you guys can flip-flop. So if you would like, you can label this. This is UV radiation. So ultraviolet, okay, sunlight basically. So UV radiation, that's coming into the earth. Some of that sunlight is going to get reflected. And that's why we have these two arrows, okay? So this is reflected by particles in the atmosphere. Again, up to you if you want to write any of these labels. And this is reflected by clouds. All right, so the next part then is once it hits the ground, it's going to be converted into infrared radiation or heat, okay? And so we're going to write or color that as red. And some of this heat's going to go back to space and some of it is going to stay here on Earth. So infrared. And then what ends up trapping it is the atmosphere, or the greenhouse gases in our atmosphere. And so if you had wanted to color the background blue here, you could. That's what they said, but you don't really need to. So the heat then is what it gets transferred to once it hits the ground. And that's why on a sunny day, if you feel something that's been laying out in the sun, it feels warm because all that sunlight gets transferred into heat. So once you're done with that, I'm going to have you put your colors back up front, and we're going to start something that we're going to finish tomorrow.